Welcome everyone to another QuantMinds webinar. I'm Matthew Dixon, the panel moderator. I'm an assistant professor of finance at Illinois Tech, and I'd like to welcome panel David Bello, senior machine learning researcher at Liquid Capital Group, Fed Award, local search model at Google, Jan Peleg, founder at Deep Trading, and Elijah De Palma, quantitative research analyst at Charles Schwab Investment Management. Today we'll be discussing deep probabilistic programming in finance. We'll be live tweeting this webinar, so you can join in the conversation using the hashtag #QMWebinar, QMWEBINAR. Now, if you have any questions during the presentation, you can send them to us using the Ask a Question on the left of your screen or by tweeting us. So with that said, let's get started. So the first question that we'd really like to address as a panel, and I'm going to pose this to Tyler here, is how does deep probabilistic programming differ conceptually from the classical frequentist statistical view and machine learning techniques that many people are familiar with today? So Tyler, do you have a comment there?
Oh, sorry.
David,
yeah,
do you like to
DPP. I'll take this for a sec. DPP differs from your standard machine learning techniques in that it's Bayesian. Most of what you've seen for ML is usually frequentist, which means primarily it's interested in the maximum likelihood of the parameters, whereas Bayesian approaches tend to deal with the entire posterior distribution of the parameters. And what this means is that frequentist approaches often substantially understate the uncertainty in the model itself, whereas Bayesian approaches do not. The flip side of this is that Bayesian approaches tend to be much more computationally expensive because you have to carry around a whole distribution rather than just a single point of your parameters. And DPP extends this Bayesian approach to deep approaches, the sort of thing you might know from like deep neural nets and the like.
David, what are your thoughts on the frequentist versus deep probabilistic programming?
Well, basically, I would say the novelty in deep probabilistic programming is the fact that instead of having for the practitioner a simple model or just one library in which you can implement just one type of model, here basically we're going towards the use of programming language, which integrates the notion of Bayesian model, of computational graph, and you can develop in a much easier way than before new models or combines models together. So basically we're going way further than just the simple type of modeling that we were doing before. The other aspect of it is that within the same language now, you can have a different type of inference algorithm. As mentioned before, basically it's pretty, it's harder to do Bayesian computation rather than just the traditional point estimations that we're used to in the frequentist approach. And there are many different types of algorithms we can use, and most of the new probabilistic programming language try to offer many algorithms at the same time so that we can test and try different approaches.
I see. Yeah, is it, are there sort of challenges with the way that sort of machine learning or deep learning is being used today?
Yeah, I want to address this problem from a more practical point of view. When it comes to actual quantitative trading and financial trading and applying models, machine learning models or Bayesian models whatsoever, those models, as good as they might be in terms of accuracy or loss or all of those measurements, sometimes they tend to be not robust as you think they are. And one of the most common misbeliefs that I've seen is models is relying on model accuracy. If you go on Cheval, you'll see people beating each other on the epsilon over who has better accuracy over their data set. But in real life, even if their data set actually represents real life and the real distribution, the models themselves tend to be, might not be as robust as you think. And in finance, a not robust model might, even if you have, let's say, 90% accuracy, which is phenomenal, you can still, in the 10% accuracy that you are okay with not being right, you can lose whatever returns that you did have in your 90% accuracy before, and that's a problem. So Bayesian deep learning actually solves this problem from because when using Bayesian deep learning, you can measure the uncertainty in the model, not just from softmax or entropy, or all of those things that are, around the model, from actually inside the model, because you're carrying the distribution inside the model as well and propagate the gradient to optimize the distributions, and not just one single point of weight, allowing you to do real statistical inference. And this is extremely crucial in finance and quantitative trading as a whole.
Yes, I agree. So the interpretation of the output of machine learning methods as being probabilistic is questionable, and the flexibility to represent distributions and uncertainties in the parameters simply isn't there in techniques like scikit-learn and TensorFlow. So moving on to the next question, let's discuss a little bit more about the importance of the computational graph. We've seen the computational graph being used in TensorFlow as a way of scaling, but why, Tyler, would you like to maybe say a few words on the benefits of that as a data structure and software?
Sure. So if you're familiar with Spark and some of these other systems, Caffe is another one, TensorFlow also looks like this. What you usually get out of these systems is basically the node of a graph. You get these reusable chunks of code that do something like, build a random forest or build some specific model, and then it's up to you to take the inputs and the outputs of that model and connect them to other things. This results in a lot of this being effectively stranded, so the models don't really know anything about each other. So if you consider something like what a mortgage model looked like when we built these for RBC, you would have an interest rate model that feeds into a housing price model, that feeds into a mortgage Markov chain model, that goes to a severity model, and so on. And you have this kind of directional flow of the information. And you also have missing data at every point along the way. So one of the things that's really important to be able to do here is to try and link this up and treat it as a whole. So one of the main sources of inaccuracy is that you may have transitions from, say, the current state to the 30-day delinquent state, and similarly going back the other way. And if you're fitting them independently, then you can pretty easily, just due to noise, get this systematic shift of too many people going in one direction and not enough going in the other. So you really need to try and treat these all as a coherent whole. So it's a computational graph both because the computational systems it's built on demand it in terms of code reuse and optimization, but also because it makes the fundamental model itself much better to treat it as a whole.
David, what are your thoughts on the use of the computational graph? And we have a slide here in the background, just with a simple example of a beta Bernoulli model from Edwards. But what could you say a little more about the graph?
Well, I think on top of the fact that you can indeed treat the model as a whole and explicitly represent some dependency even in between remote parts of your model, the other advantage is also in terms of computations. basically by representing your model as a computational graph, you explicitly create a model that you can parallelize. So in terms of speed of computations, it comes with a very big benefit, because before that, basically you just wanted to run your model one after each other, presumably on a very simple architecture, so that was very slow. And if you had a lot of data to process, basically it would take ages. The difference here is that you explicitly know where are the different computations that you're going to make, because you can follow the graph or infer that from the graph, and basically split that up onto many cores, many GPUs, whatever technology we use now. So in terms of speed, that's very important. In terms of modeling, basically, the advantage from a practitioner is like, basically I can iterate over many ideas per day and try different possibilities, which were almost impossible before having this kind of computational graph before. So especially when you look at financial market data, for example, in the world of high frequency trading, where you're going to have millions of data points per day to deal with, running and estimating one single model would take ages. With this kind of decomposition, now we can run over a lot of different possibilities, compare models between them. So in terms of speed, that's a massive benefit.
I see. So that's so there are benefits to not only to the integrity of the model, but also to the scalability on modern accelerator platforms and so on. So let's talk a little bit more about the tools and some of the methodologies and applications. You've already mentioned there high frequency trading. Say a little bit more about the sorts of tools that someone or one might use to for these sorts of Bayesian inference problems with graphs.
Actually, on the market there are plenty, and the problem is not new. There's been when you look at all the probabilistic programming language we have on the market now, it's literally dozens of them. Things evolve quite a lot, and with new libraries like TensorFlow, basically we had basic components that we can reuse basic techniques. TensorFlow by itself is just a graph of tensors, so that's something you can apply in many different fields, and obviously it's something that you can reuse a lot in more advanced modeling framework. There are a lot. There are old tools, new tools. For example, I'm sure everyone knows about Bugs. That was a tool for Bayesian modeling. It's still. We can even include programming language like R, which is it became more like a generic programming language, but at the beginning it was really focused on statistical analysis. Now we have more advanced tools like Stan, for example, which is a Bayesian modeling framework with its own language. So the specificity of this, it's focused on Monte Carlo sampling, even if the latest version includes also variational methods. So they're trying to expand to new techniques. And more recently, we have Edward, which is based on TensorFlow. So it can be used directly from Python, in which you can. You were showing the slide on the beta Bernoulli with the beta Bernoulli example. Actually, the two little lines of code are from Edward. So you can. So the difference with Edward, it's a Turing complete language as well. So you can include probabilistic representation of your model, but you can also include deterministic computations, the usual one, and build a computational graph based on that. The small difference with the new systems is that they're going to try to optimize the computations on this graph and try to find the most efficient distribution of the computations if you use GPUs, for example. So we're going one step further compared to the previous systems, and they also offer much more flexibilities. For example, in Edward, you can mix a deep learning model, neural networks, and other probability distribution, more classical one. So you can explore much more model than what you could do with Buzz or even with Stan. So little by little, we see improvements, a lot of improvements in the quality of these languages and in the kind of problem they can capture.
That's very interesting. Tyler, what are your thoughts on this?
Yes, so as David mentioned, you see lots of people using Stan. You see Edward coming along, which seems to be more complete and more optimized. One of the things people are going to use these to do a lot is construct neural networks. And neural networks are this very general class of model that also just happens to be quite efficient to implement computationally on modern computers. They sort of break up and you can split them over different chips and so on. What Edward really brings to the table is the ability to avoid reifying the graph, which is that you don't have to go through and sample all of these distributions. So if you look at the slide in front of you, you'll see this is an example of a very simple neural net using Edward, but notice that the weights and the biases are all normally distributed. And unlike in what you might work with in other systems, if you're working with Spark or something like this, you'll actually just draw a sample from that distribution and feed it in and use that to get your neural network. The thing that Edward is going to do is it's actually going to feed the entire distribution in and process the entire distribution through the neural network. And so in the end, you're going to get something that looks a lot smoother. You'll get effectively what you would have gotten by doing some enormous number of individual samples here. And again, going back to the very first point we made, that this helps you to get the distribution of the parameters in a way that renders the models a fair bit more safe than a typical frequentist model might be.
So you're saying that rather than using cross-val with a point estimate, you could use and TensorFlow, for example, you could use Edward and the probabilistic representation of the priors on the weights.
Right, exactly. It would perform the entire transformation of the probability distributions using the convolutions and various other approaches, and in a lot of cases would be able to spit those out symbolically or in its internal representation of the symbolic distribution itself, rather than spitting out some large number of points that are approximating that distribution.
That's very interesting. Yeah. What are your thoughts on this topic?
So YM33, which is over Theano, and Edward, which is over TensorFlow, had been mentioned a lot. But I just want to say that those types of Bayesian neural networks are not that different from regular neural networks. As you take your normal decent neural network that is running on top of whatever framework or whatever hardware that you want, and you put the right constraints over the sampling of the weights or the optimization or sampling from the network itself, you'll get a Bayesian neural network. So those two frameworks are optimized for Bayesian neural networks, but again, Bayesian neural networks can be implemented as well in other frameworks, such as Keras. And Keras, for those of you who are not familiar with, Keras is a framework that calls itself Deep Learning for Humans. Its goal is to democratize as much as possible deep learning, to make it as as easy as possible to do deep learning. And in Keras, if you do want to implement concepts of Bayesian neural network or some sort of constraints over the gradients, it becomes very, very easy to do so. And there are implementations online for measuring uncertainty or dropout in test time in Keras as well, and sampling weights from normal distribution or sampling the whole network in the Monte Carlo simulation. All of those things can be implemented and are implemented in Keras as well. So although Keras is not only for implementing Bayesian neural network or probabilistic programming, Keras is fitted as well for doing those types of things. And I think it was mentioned because Keras makes complex things sometimes much more easy and accessible.
I see. Well, there's seems to be a number of overlapping functionalities provided by different tools and software layers. And with that, let's talk a little bit about, how does somebody with programming skills, Python or Aura, get started with deep probabilistic programming? What would be your sort of top tips, David?
Oh, that's a very good question. I would say or if I can give an advice to junior quants, is really to start with the basics in machine learning, try to understand both the frequentist and probabilistic approach, have a good understanding of, I would say, the story behind each model. I mean, even a simple linear regression has a very interesting story to tell. And then why there could be benefits in going more probabilistic or Bayesian, even in a simple linear regression again. So that's the first thing I would say for junior quants. Then, well, there are so many tools, as we say, on the market now that basically it's just a matter of trying a few of them and really looking for what fits the best. But the truth is, I have the impression that the most recent tools are in any way so much better than the previous generation that there is no need to try all things. So things like Keras, Tan, Edward, TensorFlow, which is Keras is based on this, MXNet, etc. All these framework actually are the first tool that people can start using. On the other hand, when it's about modeling this kind of financial data, in many cases, we don't need to have extremely complex model at first. So the second advice I would give to junior quants is really to not to try to use a super deep Bayesian deep learning model just because it's very fashionable, but rather to try to see what can be captured, what the data tell, and where do they come from. And that's something, the big mistakes which is done by most of the junior quants, try to just push the data into a neural network or into a complicated Bayesian model, and at the end of the day, we just have nothing. And that's basically what I've been saying at the beginning on robustness of the model. I mean, we're back to this problem. So I would say it's just really to understand basic models at first, and then things will come naturally, because at some point you say, hey, well, by the way, I've got this point estimation, but what if my point estimation was not that great? What's the uncertainty about it? So I can represent that by a probability distribution, and that's where the Bayesian reasoning come into the game.
I see. Those are great tips, and I'm sure that there'll be further questions about that. So In wrapping up our webinar so that we can have plenty of time for discussion and questions, the question I think which is on our minds and I'm sure everyone's is deep probabilistic programming going to be the future? Where does it live in our tool set? Which applications do we really see that this is going to rise as a prominent technique for risk modeling trading? What are your thoughts on that, Elijah?
Hi, Matthew. I have a preliminary comment. There's a fundamental distinction espoused in research by Judea Pearl and his colleagues that human knowledge is organized around causal relationships, not probabilistic relationships. And the traditional Bayesian approach of expressing prior knowledge as prior probabilities is perhaps too crude and does not adequately capture the causal manner in which people store information. The big paradigm distinction with probabilistic programming from frequentist statistics is that the probabilistic graphical models can be used to impose a structural model for causal inference. And that's regardless of the underlying probability distributions on the model parameters, whether they be Bayesian or non-parametric. And within this context, we should, to quote Judea Pearl, think nature, not data. In other words, an algorithm that captures reality must impose a causal model that's more fundamental in a sense than the data itself. And probabilistic programming offers one approach. To directly address your question, for large fund managers, so less nimble than smaller hedge funds, the key barrier to entry is acceptance by senior business leaders who generally do not have a technical background and also have a lingering memory of the role of quant models in the 2008 global financial crisis. Thus, key requirements for senior business leaders are clear interpretability and industry-wide consensus acceptance. On this latter point, we have seen some progress as last year the CFA Institute announced the inclusion of big data analysis and machine learning topics into their curriculum beginning in 2019. But interpretability is still a key issue and a big barrier to acceptance for the probabilistic programming.
That's very helpful to have that perspective. Thank you, Elijah. Tyler, what are your thoughts on trading applications, given your experience on Wall Street?
Right. So I think if we're going to talk a little bit about what does the future of this field have to look like, I would say the current state of machine learning and just model building in general is basically where physics was pre-Newton. It kind of like you have some things that sort of seem to work, but nothing really fits together properly. DPP, like these sorts of approaches are clearly moving us towards what the end state of mature machine learning has to look like. The current situation looks a lot like Spark or Caffe, where you have some black boxes that kind of do their thing, and then you try to link them together. These need to be linked together, as Elijah mentioned, in a causal way, and also so that they can essentially try to cancel out the uncertainty in each other. You can think of the way that like a Kalman filter works in your car, where it's trying to find its location. It has GPS, but it also has a speedometer, and it knows which direction the car is pointed. And it integrates all of this data together to give you a much better estimate than any of them would be able to produce individually. Now, where this falls a little bit short is actually one of the things we did intensively for the mortgage models that we built at RBC, which is that the RBC models had essentially nothing provided by the operator. Like you didn't really pick anything. You just gave it a computational budget and some data, and it sort of grew the model, like progressively adding effects and checking them with information criteria and so on. And these are nice both in that they're very inexpensive to produce, but they're also very easy to defend. The regulators ask you, why did you make this choice? The answer is, we didn't. It was made automatically based on some very basic criteria that are easy to explain. And Edward is Turing complete, so something like this is clearly possible, but the authors themselves remark that this is, in their view, the major deficiency left in this field. So likely the next generation will include a lot more logic that makes this sort of thing easier, and there will be a lot less of this, hand plugging in parameters and things like that.
Thank you. And David, given you're working, in HFT, could you have different constraints than say Elijah in investment management. What are your thoughts on deep probabilistic programming for market making and for HFT firms and algo trading in general?
I think the main benefit now is rapid prototyping. Really, most of the ideas we have in high frequency trading, they just don't work. So we've got plenty of ideas just every day. But many of them they're just not profitable at all. So we have to iterate very quickly. And the thing is, with this kind of language, it makes our life just easier. We can spend like a few hours on each ID and backtest that quickly and see if we're going in the right direction or not. So it's just saving time in this kind of domain. And the thing is, patterns in the market change quite rapidly too. I mean, you can have an algorithm making money, being profitable for 3 months, 4 months, and then suddenly it stops. Why? Well, because maybe you have a new participant in the market. Maybe you have maybe an exchange change their technology a bit. They have a faster computer. Whatever. I mean, everything can happen. You have to change your model. You have to adapt your model. Sometimes just by refitting the parameters, but many times you have to invent something new or something slightly different, and you need tools in which you can describe machine learning model very quickly, test them very quickly, and I think that's the benefit we see from this new probabilistic programming language, which we didn't have before, honestly.
Well, I think we just got time for one final closing comment from Yam on this before we move to the Q&A.
Yeah, I think that more than in finance and more than in other fields, I think that math and probabilities and statistics exist for hundreds of years, and I think they bring a lot to the table to many fields and to whatever that you want to apply them. And having a more statistically right, you can call it this way, model is much better and is going to yield much better results, both in terms of accuracy and uncertainty, and actually proving stuff into the future, and then a model that are kind of black box to us. And I think that's worth mentioning, apart from the practical uses of those models.
Well, thank you very much, panel. This is we've touched on some great talking points here, a lot to think about, and now let's move over and give the audience now an opportunity to ask questions. So please do post those questions if you haven't done so already. And I'm just going to start picking questions. And so the first one that I have is, how explanatory is deep probabilistic programming compared to, say, linear regression? David, Tyler, Yam, do you want to take that question?
I'll jump in with a little. So, go ahead.
No, it's okay.
All right. So first of all, linear regression obviously requires linearity, which very often you don't have. And so for a lot of modern models, like the main source of error you have is your linearity condition is broken. So a lot of mortgage models, they're, as an example, like mortgage models would be logistic regression, so they're linear in logit space, except that the data is never really linear in logit space. For instance, with massive disincentive to prepay, like if somebody prepaid, their interest rate would go up by a lot. That doesn't drive prepayments to zero, no matter how bad the disincentive is, and this breaks your logistic assumption. So, you need something that's a little more flexible and can fit curves of different shapes than just, straight lines and logistic curves and things. So often this is done with deep models that have a couple of different layers, and then you can get these much more accurate fits, and it reduces your error quite substantially.
David, do you want to comment on that? Or should we move on to the next question?
No, just to say that actually we have exactly the same problem in high frequency trading. That's most of the situation is just not linear enough to fit in a linear regression. We just, we end up using the same kind of solutions in which we have to use more complicated problems. And I would say the Bayesian approach is more like I have many models, and at any time I want to choose one of them because I have a main model which is going to work most of the time, but as soon as I reach this corner condition, that's this very edge condition, well, I want a different model to kick in, and this kind of deep model can capture this situation. So it's practically the same.
Right. Elijah, is that a sort of fair representation of your experience with limitations of linear regression and explanatory power of it?
I think so. No comment, Matthew.
Okay, so then let's move on to the next question, and do keep these questions coming in. So, the next question we have is to any of you, what are your thoughts on combining DPP with Riccardo Rebenati's approach to coherent stress testing? If you remember a while ago, that was a topic that came out. Any ideas on where these sort of two ideas overlap? Are they methodologically, the same, or is there something conceptually different here? David, Elijah, are you able to comment on Riccardo Rebenati's work?
I'm afraid no. I'm not familiar with this work.
Yes, I think if I remember correctly, the challenge here, if I remember correctly, Rebenati is using the Bayesian belief networks. I'm not too familiar with that either, but clearly, if Rebenati's work is based around Bayesian belief networks, then of course the idea of building with causal relationships, and then clearly the idea of stress testing, stressing the inputs, is exactly the type of approach that is provided through these graphical models such as Edward and Stan. So let's move on to the next question, since we're running out of time here. So can evolutionary processes and algorithms solve the causality problems? Just quickly on this one. Any sort of quick answers here? We've got a couple more questions to get through in the next 5 minutes.
I think the answer to this is not without something else being added. One of the major issues with causality is something that it often shows up as, for instance, collinearity problems as well, right? Where you may have 2 or 3 different regressors, only one of them really causes the effect, but the others are highly correlated with it. So let's use a really stupid example. Odds of just dying this year versus correlated with like the income of your parents the year you were born, right? Like these are clearly both highly correlated with age because income has just been rising over time, but one of them explains the effect, the other one does not. And so evolutionary processes have the same problem that most other models do in that they'll just pick up strength of effect, but they actually don't know the difference between causal effects and things that are just correlated with causal effects. So in some sense, in order to disentangle this, you kind of need something more than that.
Yeah, in my opinion, I think that evolution, if I may, I think that the real advantage of evolutionary processes or algorithms is to actually optimize the function that you have no whatever prior knowledge about. And by doing so, you can embed into your fitness function some sort of measurement of causality or correlation. There are a couple of nice works that have been published, even I think recently, last year, about evolutionary processes being some sort of isomorphic under a couple of constraints to gradient descent of going up, not descent. And those types of works are really remarkable in their way of optimizing functions without any prior knowledge, without it actually being even differentiable. And so I think that if you do have the processing power to simulate, to perform many simulations, then evolutionary process might be a very powerful tool.
So just one final question here. I think in the interest of time, we've got a couple more minutes. So that's RNNs, the financial time series in with Bayesian inference. What's the advantage of that over classical econometrics methods? David, do you have or Elijah, do you have any comments on that briefly?
Well, I think we're back to the original benefit, in fact, of Bayesian models that we're mentioning before. Basically the fact that you can play with prior knowledge and also play with the entire probability distribution rather than having a point estimation like it is in the classical time series model. Is a great benefit. So within the same model, you can in fact have integrate all the space of parameters and have some probability distribution on the most probable of them, which is at the end of the day what you want to have from a Bayesian approach. So it gives much more flexibility to your model than the traditional approaches.
Very good. Well, we're out of time here, and I do want to make sure that the other questions get answered. So we'll follow up with you if you have submitted a question after the session. So with that, we'd like to thank the panelists here who are joining from 3 different continents today, and trust that this was a useful webinar for all of you. Thank you for joining.